All right, hello everyone and welcome to our page 39, the first page of semester 2's notes. So today we're going to take a look at inverse trigonometric functions and talk about some of the properties that will be helpful to us in exploring this topic. So first thing is we got to fill in this text up here. It says a function is a blank if and only if it is a blank function. So we know that from the beginning of the year, this is way back at the beginning of the year, we know that a function is an inverse if and only if it is a 1-to-1 function. And what that meant is that if you took a function, we know that to be a function, you just have to pass the vertical line test. But if you are an inverse function as well, then you have to pass the horizontal line test, which is what 1-to-1 is. 1-to-1 means that it can pass the vertical and the horizontal line test. Well, if you think about sine, cosine, and tangent, they are not 1-to-1. And I can show you that actually right here. Let's flip to this page real quick. We can see that right here. If you were to look at the sine function and think about what sine does. Sine, we know that it starts at 0. It goes up, down, down, and then over here it would repeat kind of the same way. We know that it would go like this, this, this. So we have a function that ends up looking something like this. Well, it definitely passes the horizontal line test, right? If I took this horizontal line, if I were to do that anywhere on here, no matter where I went, I would only touch it one time. But as soon as you do a horizontal line test, I think I said horizontal line the first time, I meant vertical. If I do a horizontal line test here, you can see it hits once, twice, 3 times. So we know that this does not classify as a 1-to-1 function because it doesn't pass the horizontal line test. It's only a function because it passes the vertical line test. So that's what that says there. Sine, cosine, and tangent are all not 1-to-1 functions. However, if we take the domain and restrict it to a certain interval, they do have inverses. And that's what this whole topic is about, is if we take sine, cosine, and tangent and cut them off at the ends and say we're only going to look at it from a certain spot to another certain spot to create a 1-to-1 function, it works. So let's go ahead and talk about that. So we have sine, which if we were going to write sine as its function form, we know that's f of x equals the sine of x. So that would be its parent function if we're going to talk about that again. So the domain for our inverse, if we are going to find the inverse of sine, what we end up doing is we restrict sine from negative pi over 2 to positive pi over 2. And let's again take a look at that one on this side. Look what I'm doing right here. I'm restricting sine here to here. And see that when we do that, the only part of the function that we're now looking at is this piece right here, which does create this situation where we can actually, hey, I screwed up that graph earlier. I'm like, wait, that doesn't work. Hold on, let me regraph this and draw this the correct way. What this should have looked like earlier, that I graphed it as if this was pi and this was negative pi. That's not what I meant to do. That's okay though. Let's graph it correctly now. If we're graphing it that way, we know that when we get here, it's at 1, and then over here it would have been at 0. And it would have been like this, -1, and then over here it would have been at 0. So that's what the function would have looked like had I graphed it correctly. Okay, so now with that in mind, if I restrict it here and here, now you can see that that little piece, only the middle piece, if we only focus on this spot right here, that would pass the horizontal line and the vertical line test, meaning that it is a 1-to-1 function. So that's why we're going to do that restriction like that. The range for the parent function still remains the same. It's still -1 to +1. And the inverse function can be written in one of 2 ways, and this is important. We can write it like this, arc sine of x. That is one way to write the parent function, or we can write it as sine to the power of -1 of x. That also means sine inverse of x. Those mean the same thing. They are identical in meaning. It's just 2 different ways to communicate the same idea. different levels of math use it differently. For example, you might in calculus see it one way or another way to create less confusion. And it a lot of times comes down to how the teacher wants to do it. But I'm going to use both just so you get comfortable seeing both. All right, cosine. Cosine is a function represented as the parent function, cosine of x. And its domain gets restricted a little bit differently. Instead, we restrict this from 0 to pi. And again, let's take a look at why we might do that. If we were to graph this the cosine function, we know cosine starts at its maximum, goes down to its, nope, doing the same mistake I made last time, goes down to the midline, then down to the minimum. And then over here, it would probably come back up. Over here, it would be like there. So this would be our cosine curve. So again, if we take it and restrict it, we're restricting it from 0 to pi. You can see that by doing that, now I've created a one-to-one situation again that works. So that it creates an inverse function. So that is how we're going to do our cosine function. Again, the range here doesn't change. It's still -1 to +1, minimum to maximum. And in this case, very similarly, we have arc cosine of x, or we can call it cosine -1 or cosine inverse of x. And last but not least, we got our tangent function. Our parent function could look like this, the tangent of x. The domain of tangent looks very similar to sine, except one small change. We have these parentheses instead of our brackets. And again, we can see why that is. Let's come over here. We know that for the cosine curve, what normally happens is that we start at 0, 0. Let me stay consistent here. We start at 0, 0. We would have an asymptote here at pi over 2 and negative pi over 2. This would go up. This would go down. Over here, this one we would see something coming down here. We'd see something coming up here. Something like that. Again, now we're going to restrict it. We're restricting it at this asymptote and at this asymptote. So I can't put brackets on negative pi over 2 because it's an asymptote. We can never touch it. So it's a parenthesis there. But you can see that one tangent curve, if you focus only on this single tangent curve, it already was a one-to-one function. It's just that when you add all these other pieces in, the tangent on the left and the right, that screws it up. So if we only focus on one tangent, it does create a one-to-one function. So that's what we're going to do. Notice that the domain here, we said negative pi over 2 to pi over 2 is good, but the range is a little bit different because where sine and cosine stopped and started at -1 and +1, tangent does not. So when we go over here to do this, the tangent has a range that's a little bit different. Its range is -infinity to +infinity because it goes up towards that asymptote and never stops. So a couple slight changes that we got to keep track of when we do our tangent. Over here, though, this part's the same. Arctangent of x or tangent inverse. That is an ugly negative. Tangent inverse of x. You can choose which one makes more sense to you. I'm going to use both so we get in the habit of seeing both of them. All right, so coming down here, let's take a look and solve some of these. It says create a table of the sine values from the unit circle to determine the inverse and its solution. So we know that we're looking at arc sine or inverse sine. So we need to know all the sine values on the unit circle from this space right here, from this negative pi over 2 to positive pi over 2. Those are all the things we need off the unit circle. So we know that negative pi over 2 would be the fourth quadrant and a pi over 2 would be the first quadrant. In other words, if you looked at like the unit circle, right? Here's our unit circle. I know that 0 to pi over 2 is this section here, but 0 to negative pi over 2 is that section there. So I'm really only focused on quadrants 1 and 4 when we're doing inverse sine. So let's see if we can come up with a list of those values here. I'm going to create like a little table here. We'll put our x and our y here. So we know that if we start at the top of our unit circle, we've got pi over 2, we've got pi over 3, pi over 4, pi over 6, and 0. And let's actually just do this. This might be a little bit easier. I'm going to run out of room. We'll make this our negative ones. So then if we go down negative, we got negative pi over 6, negative pi over 4, negative pi over 3, and negative pi over 2. So we got to think about our unit circle and come up with what's going on there. These are two separate tables. Just put that there so we can clearly see that. So remember, sine is always represented by the x coordinate. Nope, that's wrong. The y coordinate. Sine is represented by the y coordinate. So if we have our unit circle, we could look at our unit circle and figure out what's going on there, or you can hopefully do it from memory. Hopefully you haven't forgotten it over winter break. We know that the y coordinate pi over 2 is 1. The y coordinate pi over 3 is square root of 3 over 2. The y coordinate at 4 is square root of 2 over 2. Pi over 6 is 1 over 2. At 0, the y coordinate is 0. Now we come over here to these negatives. Negative pi over 6, which is really 11 pi over 6, was negative 1/2. Negative pi over 4, which was the same thing as 7 pi over 4, is negative square root of 2 over 2. Negative pi over 3, which is the same thing as 5 pi over 3, is negative square root of 3 over 2. And negative pi over 2, which is the same thing as 3 pi over 2 on the unit circle, is negative 1. So now we can kind of use this to help guide us here. So this first one says, find the arc sine of negative 1/2. What that means is we're going backwards. So instead of me saying, what is the sine of pi over 6? What is the sine of 150 degrees? Instead of doing that, now we're saying go backwards. When? This question literally says, when is sine negative 1/2? When is sine equal to negative 1/2? That's the question that's being asked here. So what we need to do is we need to go look on here and see, okay, where do I have a negative 1/2? Well, I have a 1/2 right here, but it's not negative, so that's not going to be the one we want. So negative 1/2 is going to be right here. So we know that we need to use this one, which means that our solution is going to be that it happens at negative pi over 6. And that's all we're doing. Now, the reason we have to restrict it, I want you just to be mindful of this. If you have that unit circle in front of you, you would notice something. Negative 1/2 happens in two places. It happens at what we would call 11 pi over 6, but it also happens at 7 pi over 6. And that's why we have to restrict it, because we don't want two answers. We don't want to say 11 pi over 6 and 7 pi over 6. For it to be a function, it has to be only one answer. So we only want to choose 11 pi over 6, or in this case, we're using the negative, so negative pi over 6. Remember, negative pi over 6 and 11 pi over 6 are the same thing because they're coterminal to each other. So let's try this one. It says, when is sine equal to square root of 3 over 2? So yet again, we're going to come over here. We're going to look for square root of 3 over 2. I can see positive square root of 3 over 2 is here. Be careful not to mix that up with the negative. So I know that happens at pi over 3. So our answer is positive pi over 3. And we got one more. It says, when does sine equal 2? Well, that's an issue because we know that these numbers right here, these three numbers, negative 1/2, square root of 3 over 2, and 2, that represents the range of this function. So for sine, the range had to be between negative 1 and 1. Negative 1/2 is between negative 1 and 1. Square root of 3 over 2, it comes out to approximately like 0.7 something. So it's between negative 1 and 2. 2 is not between those numbers. So the range is, I'm going to write it like this, is negative 1 to 1. So 2 doesn't work. We're going to write that just for that one so we can see how where that came from. But in the future, all you're going to write is D and E does not exist. Those are the answers that you're going to write. D and E. All right, so you can see that we could do that with the table. That's great. It does help a little bit when you're first getting used to this. But again, as you're remembering this unit circle and bringing it back into the front of your brain after this long break, we're just going to take that unit circle and apply it now. Simply think about what's happening on the unit circle. Don't worry about drawing the table. Look at your unit circle. So what I mean by that is if I look here, this one says now we're focusing on cosine. Cosine inverse on arc cosine. So cosine inverse. When does our cosine equal square root of 2 over 2? Well, let's look at cosine. When we're thinking about the unit circle for cosine, so here's our unit circle sketch. We know that we're only focused on 0, 0 to pi. So instead of it being quadrants 1 and 4, it's quadrants 1 and 2. Cosine uses 1 and 2 for its answers. So it's a little bit different. So you got to kind of keep that in mind as you're working through these problems, not to mix them up. So we know that negative square root of 2 over 2. Cosine is the x values. So this is the x coordinates. And so we want to ask ourselves, when does the x coordinate give us negative square root of 2 over 2? Well, I know that the negative x is going to happen in quadrant 2. So I know that this first one comes from quadrant 2. So this is kind of my thought process as I do this. I'm going to write out what quadrant it comes from. And then I'm going to think, okay, well, in quadrant 2, square root of 2 happens at radians of 4, right? We know square root of 2 happens always at pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. So I know that my answer is something over 4. And then we just address. We know that in quadrant 2, the number on top is always 1 less. So we got 3 pi over 4. And if you look at your unit circle, you would see that at 3 pi over 4, we do get negative square root of 2 over 2. In this one, we know that positive 3, well, if it's positive, it would have to come from quadrant 1. But this number is too big. It's bigger than negative 1 to 1. It's outside of our domain. So we know this is the situation where we say it does not exist. So if it's outside negative 1 to 1 for sine or cosine, we have to say does not exist. And our last one here is arc cosine of negative 1. That's an interesting one. We know that the 1s and the 0s always pop up on the poles of our unit circle. So in this case, it's going to be one of these 3 spots, right? So which one has an x coordinate of negative 1? Well, that's going to be this one right here because we go left 1 unit. So that represents pi. All right, and example 3 takes us to that last trig function, which is focusing on using tangent. Tangent is a little bit different in the sense that there will never be a does not exist because we said that the range of tangent is negative infinity to infinity. So there's always a solution for tangent, which makes it a little bit trickier that we can't ever just eliminate them. Coming on here, let's draw a quick unit circle sketch again, just like we did the others, talking about where this would be. So again, we're focused on negative pi over 2 to positive pi over 2. So very similar to sine. It's always going to have solutions in quadrants 1 and 4. 1 being the positive, 4 being the negative solutions. So coming down here, let's see. Arc tangent of square root of 3 over 3. Now here's where it gets a little bit tricky because tangent doesn't just work beautifully, right? Tangent isn't just look at the x or just look at the y. Tangent is that we take the y divided by the x. So we have to really think about where this came from and how we got here. So for example, in this one that says square root of 3 over 3. We know that originally that had to come from having something like where there were 2's involved, right? Square root of 3 over 2 and 3 over 2, but those aren't numbers off the unit circle. So we know that something definitely had to get adjusted into that. Maybe a good key to help you here might be drawing just quadrant 1, right? Thinking about what's happening in quadrant 1 and drawing it right here. So in quadrant 1, we know that at this point we have 1, 0, and up here we have 0, 1. Here we have square root of 3 over 2 and 1/2. Here we have square root of 2 over 2, square root of 2 over 2. And here we have 1/2 and square root of 3 over 2. Since we're trying to take y divided by x, we can look at those and see when would that happen. When would I take y and divide it by x? And as you get better with this, you'll start memorizing. There's 3 answers here that are really important to remember. 1 divided by square root of 3. Remember, you can disregard the 2 on the bottom. The 2 on the bottoms are just going to cancel. So 1/2 divided by square root of 3 over 2. The 2's cancel, so it's really just 1 over the square root of 3. This one, square root of 2 divided by square root of 2. And this one is square root of 3 divided by 1. Well, 2 of these have really easy answers. Square root of 3 divided by 1 is square root of 3. Square root of 2 divided by square root of 2 is 1. 1 divided by square root of 3 is the one that you have to rationalize. You'd multiply the top and the bottom by square root of 3, and you would get square root of 3 over 3, which is the one we're looking for. So it's very important to remember that square root of 3 over 3 always comes from your pi over 6. That will kind of help you make this make a little bit more sense. You go through and speed up that process. So I know that this one equals pi over 6 because it's positive. For B, it says find the arctangent of -1. Well, we know that -1 only happens if it is in quadrant 4. And look at these ones that we have over here. If you look at the ones we already did over here, we know that this gives us square root of 3 over 3. This gives us 1. This gives us square root of 3. Well, we want -1. So we know it's going to be focused on this spot right here, which is that pi over 4. But it's not positive. We're going to go the opposite way. So it's negative pi over 4 would give us a spot where we get -1. And last but not least here, the inverse tangent of radical 3. Well, we did this already over here by making this little chart. It helped us. Radical 3 came from right here, which we know is our pi over 3 section. So we got pi over 3. And there are our final solutions. So go ahead, enjoy looking at that, go over it a little bit more. Again, knowing your unit circle is going to make all the difference here. If you're really stuck and you don't know the unit circle, it's probably a good reason why you're stuck. So make sure you look at your unit circle, make sure you remember how to do it, and practice that, and you'll get way better at this. Have a great day. Bye.